Hi everybody. Now we are going to see some basic introduction about the combinational logic circuits. What does this combinational logic circuit means? See, in this logic diagram, you can see that we are giving certain set of inputs and certain set of outputs here. So, giving the n number of inputs at a time and getting the m number of outputs at a time. This circuit does not depend on any other states to get us an input, or else it does not have any memory space to get the input here. Just it is getting the input directly and it is producing the output here. This is the future of the combinational logic circuit. That is, a combinational logic circuit means which has a combination of n input variables with no storage involved, and it does not depend on any other previous states to produce to give the input also. So without any usage of memory also, we will be getting the input and doing some process and producing the output here. This is called combinational logic circuits. And now we are going to see what is meant by an adder. Adder means that is the binary inputs will be summed together and it will produce the output. What is meant by this half adder means? Half adder means getting two inputs, two binary inputs and producing the output. How come with this two binary inputs is how we are calculating this means, as we have seen earlier in the number system, see this 1 2 1 plus 1 here and 2 here, so totally we are having 3 here. So if it is my first number is 0 0 0, and in the place of 1 I have specified as 1, and in the other place I have specified as 0, so the input value is 1 here. And the next place is, in the place of 2 I have specified as 1, and in the place of 1 I have given as 0, which means the input value is 2. And in the place of 1 and 2 it has been given as 1 1, which means total values of 3. So 0 to 3, 4 in 4 set of values has been specified here. Then how we are calculating this sum means 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1, in the binary it will be represented as 10 here. So 0 will be given in the place of sum and 1 has been taken as an carry here. Can you understand how we are mentioning this truth table here? Right? For this calculator truth table, now we are going to draw a K-map simplification. How come this K-map simplification represent means? In the K-map simplification, you might have seen that this A is given with the input values of 0 and 1, B 0 and 1. If it is of 0, then A complement will be specified. If it is of 1, A will be specified. Similarly, B 0 means B complement, 1 means B. Now we have to look after the carry where the 1 is available. In the place of A is equal to 1, B is equal to 1, the 1 is available. So I am searching for A is equal to 1, B is equal to 1. So in this place I have specified as 1. And in the remaining places it has been specified as 0. Right? In the remaining places it has been specified as 0. Now what I have to do is carry is equal to A is the input that I am given and B. So my output is carry is equal to A and B here. Can you understand how I am giving this A and B? Right. And next is sum. Now we have to look after this truth table, that where this 1 are available. Now we have to look after that. Where these 1s are available, in the place of 0 and 1 and 1 and 0, A is equal to 0, B is equal to 1. 1 is available, and in the place of A is equal to 1, B is equal to 0, the 1 is available. And in the remaining places I have specified as 0 0. Now I am writing sum is equal to A B bar, that is A B bar. and A bar B plus A bar B. If these two are in the reciprocal form, that is A B complement plus A complement B, means this term can be mentioned as A XOR B, right? A XOR B can be specified in this form. Now next what we have to do is, we have found a truth table and we have find a K-map, and the simplifications has been found for both sum and carry. Now for this received output, what we have to do is, we have to draw a logic diagram for that. Now we are moving on with the logic diagram. That is, A and B is our two inputs. So A and B, if it is a product form, we have to move on with the NAND gate. That is, carry is equal to AB. And if it is of XOR form, I am directly moving on with the XOR gate as sum is equal to A XOR B. Right? Please don't get confused that if we are getting the expression in the form, this can be shortened and it can be mentioned in this form. Right? Next, this full adder. What is this full adder represent means? It is nothing. We are having the same concept, but here the input variables will be of two significant fits, and our third input will be of carry from the previous lower significant position. That is A, B, C, N. This is our third input. How you are going to give input for these numbers means as of same 1, 2, 4. In the place of 0, I am mentioning 0 in all the places, and in the place of 1, I have mentioned 1 in all the places. Sorry, I have mentioned 1 in the place of 1 and remaining places with the 0, and 2, 1 in the place of 2 and remaining places with the 0. Similarly, we are engaging all the 0 to 7 input values. And next what we have to do is, we have to do the addition process, right? 0 plus 0, 0. 0 plus 0, 0. That is our first output. And 0 plus 0, 0. 0 plus 1, 1. So sum is 1, carry is 1, 0. 0 plus 1, 1. 1 plus 0, 1. Sum is 1, carry is 0. 0 plus 1, 1, 1 plus 1, 10. So sum is 0 and carry is 1. Similarly for next also, we are getting the sum is 1 and carry as 0. And for this next, the sum is 0 and carry 1, sum is 0, carry 1. Here third one is 1 plus 1 is 10, 10 plus 1 is 11. So here the sum is also 1 and carry is also 1. Now what we have to do is, now we have to draw a K-map for the same, in the same pattern. Just we have taken A in this place and BC in another form. And we have to find wherever the 1 is available, and we have to put 1 in those places, and we have to do the mapping. After doing the mapping, we have to consolidate with the expressions for both sum and carry, and then the logic diagram has to be drawn for it. This is the way in which we are implementing the half adder and full adder. And in this diagram, you might have seen that how we are using two half adders. How we are using two half adders to implement one full adder. Here I didn't move on with the full adder directly. I am using two half adders, right? That's what we are seeing in this slide, and that's all of half adder and full adder. We'll see the remaining in the next video. Thank you.